I did mention the other day the idea of the order of a group. If the group is finite, the order of the group is the number of elements in the group. We wrote, well, okay, it looks like it's absolute value of G, but don't say absolute value, say order of G. I won't write it out. Again, just verbally say it to you. If G is a finite group, then this order of G is the number of elements in G. If G is an infinite group, we say the order is infinite. Do we say this equals infinity in that case? I won't mark it wrong if you do. But more generally, the order of an infinite group is what's called its cardinality. And there are examples of what are called infinite cardinals. Different kinds of infinity, effectively. But we're not going to get into that. You'll learn a little bit about that in real analysis. What is the order of an element? Suppose A is an element of a group G. What is the order of an element? We can define such an idea. This is the order not of G, but the order of the element A. This is a little confusing. The order of A, well, you could write it as a piecewise formula. And I'm going to describe it in words. So I'm going to describe the output of this formula in words. It's the smallest positive integer n such that a to the n is the identity if there is such a smallest positive integer. If there is such a smallest positive integer. And it equals infinity if not. Okay, and again, when I write that, I'm not saying infinity is a number. I'm saying the order of A is infinite. It's not finite. It's very important that you focus on this word smallest positive integer. The order of A is the smallest positive integer such that a to the n equals the identity if there is such a smallest positive integer. Infinity if there is not such a smallest positive integer. That's essential. All right, let's look at some examples. Let's actually start with the U examples. U of n, like U of 2, where the operation is multiplication, mod n, instead of the Z examples where the operation is addition mod n. U of 2, not the band U2, but U of 2, it's called the group of units modulo 2. As a set is the positive integers less than 2 that are relatively prime to 2. It's only got one element, 1. 1 is E here. 1 is the identity. What's the smallest positive integer that you can raise this to get the identity? Well, 1. Therefore, the order of 1 is 1. This is a trivial group, okay? In fact, the order of the identity in any group is 1. Note, in any group G, the order of the identity is 1. What about the group U of 3? Group of units modulo 2. As a set, all positive integers less than 3 that are relatively prime to 3. There's 2 of them, 1 and 2. The order of 1 is 1. What's the order of 2? Not 1. 2 to the first is 2. Is it 2? What's 2 squared? 4, but wait a minute. We got a mod by 3. 4 mod 3 is 1. The identity. Therefore, the order of 1 is still 1. That will always be the case. The order of 2 is 2. No crazy looking equations so far. Next example, U of 4. Elements, positive integers less than 4, relatively prime to 4. There's 2 of them, 1 and 3. Under multiplication mod 4. Once again, 1 to the first is 1. The order of 1 is 1. 3 to the first is 3, not 1. 3 squared is 9, but 9 mod 4 is 1. Therefore, the order of 1, yes, is 1. The order of 3 is 2. We get our first weird-looking equation. That's not the absolute value of 3 equals 2. Don't go teaching this to pre-calculus students. That's the order of 3 as a group element in U4 is 2. We were doing mod 4 arithmetic. 3 squared is 9. 9 mod 4 is 1. Right, mod 4 to yourself if it helps. U of 5. Elements are 1, 2, 3, 4. Yes, order of 1 is 1. Order of 2 is not 1. It's not 2. 2 squared is 4. Mod 5 is still 4, which is not 1. 2 cubed is 8. 8 mod 5 is 3. You could also, yeah, you could also think of it as 2 times 4 there. 8. 8 mod 5 is 3. 2 to the 4th is 16. 16 mod 5 is 1. You could also think of it as 2 to the 4th is 2 times 3 because 2 cubed was 3. 6 mod 5 is also 1. You get the same answer. The order of 2 is going to be 4. How about the order of 3? It's not 1. It's not 2. 3 squared is 9, but 9 mod 5 is 4. We're doing mod 5 arithmetic now. 3 cubed is 27. 27 mod 5 is 2. 3 to the 4th is 81. 81 mod 5 is 1. The order of 3 will be 4. You could also do 3 to the 4th as 3 times 3 cubed. 3 times 2 is 6. Mod 5 is 1. You could also do 3 cubed as 3 times 3 squared. 3 times 4 is 12. 12 mod 5 is 2. It's all going to work as long as you don't make a mistake. How about the order of 4? It's not 1, but it is 2. 4 squared is 1 because 16 mod 5 is 1. Therefore, the order of 1 is 1. The order of 2 is 4. The order of 3 is 4. And the order of 4 is 2. By the way, I hope it's clear that not only does the identity in any group have order 1, but any non-identity element has order greater than 1. Though saying this would include the case where the order is infinite as well. Thinking of infinity as bigger than 1, which you would think of it as bigger than 1 if you thought of it as a number. U of 6. U of 6 is back to just two elements, right? The positive integers less than 6 that are relatively prime to 6. 1 to the first is 1, 5 to the first is 5, 5 squared better be 1. Yeah, 25 mod 6 is 1. Order of 1 is 1, order of 5 is 2. U of 7. We'll do two more examples here. 1, 2, 3, 4, 5, 6. It's got 6 elements. 7 is a prime. All the positive integers less than 7 are going to be in the set. Just like with U5, all the positive integers less than 5 are in the set because 5 and 7 are prime. Same kind of thing really happens with 3 as well. 1 of the first is 1, 2 squared is 4, 2 cubed is 8, mod 7 is 1. 2 is going to have order 3. We haven't seen an example like that yet. 3 to the first is 3, 3 squared is 9, 9 mod 7 is 2. 3 cubed, 27, 27 mod 7 is 6. Alternatively, 3 cubed is 3 times 2 is 6. Order is going to be bigger than 3. 3 to the fourth, 81, 81 mod 7. Let's see, 7 goes into 77 evenly. It's going to be 4. You also could do it as 3 times 6 mod 7. 3 times 6 being 18, mod 7 is 4. Tracking with me? Still not back to the identity. 3 to the fifth, I'll do it as 3 times 4. 3 times 3 to the fourth. 12, 12 mod 7 is 5. Still not back to the identity. 3 to the sixth. I'll do it as 3 times 5 is 15. 15 mod 7. Now we're back to the identity. 1. Four squared is 16. 16 mod 7 is 2. I'll do 4 cubed is 4 times 2 is 8. Mod 7 is 1. 5 squared is 25. 25 mod 7 is 4. 5 cubed. Do it as 5 times 4 is 20. Mod 7 is 6. 5 to the fourth, I'll do it as 5 times 6 mod 7. 30 mod 7 is 2. 5 to the fifth, same as 5 times 2 mod 7. 10 mod 7 is 3. Then 5 to the sixth, same as 5 times 3 mod 7 is back to 1. Finally, 6 squared is 36. 36 mod 7 is 1. How about that? Interesting. The order of 1, as always, is 1. The order of 2 is 3. The order of 3 is 6. The order of 4 is 3. The order of 5 is 6. But the order of 6 is 2. Maybe unexpected. Is there a pattern here? There are patterns, but it's maybe not clear what they are. One pattern that I'm just going to tell you, maybe you guessed it, is that these orders, 1, 3, 6, 3, 6, 2, they all divide the order of the group, 6. That's not a coincidence. That's got to happen. The order of an element, when it's got a finite order, has to divide the order of the group when the group is finite. By the way, all groups, all finite groups will have elements with finite orders. If G is finite, every element will have finite order. Said another way, if any element has infinite order, then the group itself must be infinite. If the group is infinite, is every element have infinite order? No. Identity doesn't. It's got order 1, always. But there's more interesting examples of infinite groups that have elements of finite order. We'll talk about those examples maybe on Friday. One more example, U of 8. This will be smaller. Positive integers less than 8, relatively prime to 8 are 1, 3, 5, and 7. 1 squared is 1, 3 squared is 9, non-mod 8 is 1. 5 squared is 25, 25 mod 8 is 1. 7 squared is 49, 49 mod 8 is 1. The order of 1 is 1, because 1 to the first power is itself. I should have put a 1 here. The order of the other elements, 3, 5, and 7, are all the same. They're all 2. There's no element of order 4, even though this has got 4 elements. The group has order 4, but there's no elements of order 4. Though the orders of the elements do divide the order of the group. That's something different than what we've seen so far. So far in all these examples, there has been at least one element that has order equal to the order of the group. 2 in U3, 3 in U4, 2 and 3 had order 4 in U5. 5 has order 2 in U6. U6 has 2 elements. 3 and 5 have order 6 in U7, which has 6 elements. But in U8, the order of U8 is 4, but no element has order 4. That's something different. It's called a non-cyclic group when that happens. If any element has order equal to the order of the group, then the group is called cyclic. Chapter 4 is all about cyclic groups. Let's now consider some Z examples. By the way, Zn groups are going to always be cyclic. They are the prototype cyclic groups. I'm not explaining why yet. Z1 just contains one element, 0. Under addition mod 1. The order of 0 is 1. Does that mean 0 to the 0 power equals 0 to the first power equals 0? That's not what I'm saying. Though in the regular number system, you could say that's true. I'm saying 0 is already equal to itself when I add it to itself by being itself. I'm not doing 0 plus 0. I'm just thinking of 0 as being the identity. What I'm trying to emphasize is the group operation is addition, not multiplication. It gets a bit more interesting if I go to Z2. First, two integers starting with 0 is the elements 0 and 1. Under addition mod 2. Once again, 0, the identity, has order 1, but what order does 1 have? How many times do I have to add 1 to itself? Or better, how many summands in that sum is going to get me back to the identity, which is 0? Well, 1 by itself does not equal the identity, but 1 plus 1 is the identity. So I've got 2 summands in the sum, being the smallest number of summands, getting me back to the identity. That means the order of 1 is 2. We're not raising to powers here because the operation is not multiplication. We are adding. In Z3, it's got 3 integers, first 3 integers starting with 0, 0, 1, and 2, under addition mod 3. Once again, the order of 0 is 1. The order of 1 is not 2 this time, because 1 plus 1 is 2, not 0. It's 3. 1 plus 1 plus 3 is 0 mod 3. Therefore, the order of 1 is 3. What's the order of 2? It's not 1. It's not 2 either, because 2 plus 1 equals 2 plus 2 equals 1 mod 3. Not 0. But 2 plus 2 plus 2 is 6. Mod 3 is 0. Therefore, the order of 2 is also 3. Z4. Elements are 0, 1, 2, and 3. Once again, 0 has order 1. What's the order of 1? 1 plus 1 is 2, not 0. 1 plus 1 plus 1 is 3, not 0. 1 plus 1 plus 1 plus 1 is 4. Mod 4 is 0. These are a bunch of 1 pluses here. They kind of look like they're all melding together there. Therefore, the order of 1 is 4, which is the order of the group. This is the cyclic group. 2 plus 2 is 4. Mod 4 is 0. 2 itself is not 0, but 2 plus 2 is 0 mod 4. Therefore, the order of 2 is 2, actually, in this group. The order of 3 plus 3 is 6, mod 4 is 2, not 0. 3 plus 3 plus 3 is 9, mod 4 is 1, not 0. The identity is not 1 here, it's 0. Yes, 3 plus 3 plus 3 plus 3 with 4 summands is 0, because it's 12, and 12 mod 4 is 0. Therefore, the order of 3 is 4. I could keep going. I'd like to do other examples, though. You got to be careful when the group operation is addition, which it will be for Zn. You got to think about adding instead of raising the powers. You could rephrase the definition of order in that case. Instead of writing a to the n and looking for the smallest positive integer that gives you the identity e, people do use this notation. They write n times a, where n is a positive integer here, a natural number, and a is a group element, as being the additive form, so to speak, of raising to a power. And this means a added to itself with n summands. There are n a's there. This is if the group operation is addition. And actually, if the group operation is addition, and if you know that, it is more traditional to call the identity 0 instead of e. You should realize that when the group is operation is addition, and you know that, and you are assuming that and using that notationally, you do typically write the identity as 0 instead of e. By the way, some people in the abstract don't use e for the identity, they use 1. But that notation, that 1, is not necessarily the number 1. Just like this is not necessarily the number 0. It's just a notation for the additive identity in a group where the operation is denoted with addition. To end class, let's look at D4 and think about the order of its elements. D4 consists of rotations, four rotations, although one of them is a trivial rotation where you don't do anything, are 0. And then 4 reflections. V was reflecting across a vertical line of symmetry. H was reflecting across a horizontal line of symmetry. D was a reflection across a main diagonal from upper left to lower right. And D prime is a reflection across the opposite diagonal from upper right to lower left. The order of the identity, as always, is 1. R0 is the identity. What's the order of R90? Raising to powers means function composition here. The group operation is function composition. What's the smallest positive power, quote unquote, of R90 that's going to bring you back to the identity? Go ahead. 4, yeah. Apply R90 with 4 times, meaning 4 factors in the product, so to speak. You're going to get the identity. Do a 90-degree rotation 4 times. It's equivalent to not doing anything. What's the order of R180? 2. The order of R270, a little trickier to see, but it is 4. The order of the flips, the reflections, what are they all equal to? They're all equal to the same thing, 2. You reflect and do the same reflection again, you get back to where you started. They all have order 2. So none of these elements has order equal to the order of the group. The order of the group, D4, is 8 as the group order, but none of the elements has order 8. This is not a cyclic group. It's also not an abelian group. U8 was not a cyclic group, but it is abelian. This is not a cyclic group, but it's not abelian. Some other important things in chapter 3 include the idea of a subgroup, analogous to subspace in linear algebra. What was a subspace? You had a vector space, like say R3, 3-dimensional space. A subspace was a subset of the vector space that is also a vector space. And if your vector space was R3, those included, well, just the origin, the trivial subspace, trivial vector space with 1 element, lines through the origin, you remember that? Or planes through the origin. Those were examples of subspaces in linear algebra. They are subsets of the bigger vector space that are also vector spaces in their own right, which does mean they are closed under vector addition and scalar multiplication. It's a similar idea with subgroups. Got a group? Is there a subset of that group? That is a group in its own right, under the same operation. You can't visualize it really. Well, you can in some circumstances, like actually 3-dimensional space is a group under addition of vectors, and lines and planes to the origin are still subgroups, just like they were subspaces. But most of our groups were not trying to visualize that way. Just like you had a subspace test, there's a subgroup test. In fact, there are 3 subgroup tests in our book. One's called the 1-step subgroup test, another one's called the 2-step subgroup test, and another one's called the finite group subgroup test. It's a little funny. The 1-step subgroup test actually involves 2 steps. The 2-step subgroup test actually involves 3 steps. And the finite group subgroup test actually just involves, well, you still need to verify, it involves 2 steps. Why the funniness with the naming? It's sort of because the first step is considered to be kind of trivial, but it does have to be done. You do have to, the very first step, you could call it the 0th step. You do have to verify your thing you're trying to show as a subgroup is non-empty. That's the 0th step, so to speak, kind of like a base case with induction. And that's why the funniness with the naming. You should also look for cyclic subgroups generated by elements. And this notation, an A with pointy brackets around it. Reminiscent of notation used for vectors in linear in multivariable calculus, actually. But it's a different idea. This is the set of all powers of A as n ranges over the integers. Very, very important kind of subgroup. Turns out it is a subgroup, and you can use one of the subgroup tests to verify that. So be looking for these things, whether in the lectures or the reading or both.